So just a reminder, test is on Monday, and the material that we go over today, the Wednesday lecture, that will be the last material that will be covered on the test. Just a reminder of what we covered on Monday. We looked at Lewis structures, Lewis models, and we wrote the Lewis symbol for some elements. We looked at ionic bonds, covalent bonds, and metallic bonds. And then we wrote Lewis symbols for ionic compounds. Then using our Lewis symbols, we figured out how we can decide how different elements combine in what ratios. Then we looked at this idea of lattice energy. And remember, lattice energy is the energy that's holding together an ionic crystal. The smaller your molecules are, the more heavily charged that they are, the bigger or stronger your lattice energy, or the harder it is to break apart this crystal. What date does the exam 4 content begin? It was the beginning of November. I'm not exactly sure the date. Just checking the test 4 folder. It should say the date right on there for our first PowerPoint. Yeah, but on top of my head, I can't remember the exact date. And then we looked at the trends here, and we put these in order from low to high for lattice energy. So we do have one more question, and it's rather a simple one before we move on to the stuff for today. Looking at these two compounds, KBr and CASE, which one has a more negative lattice energy? And so I have a poll for that. So that's where we're going to get started. So have out your periodic table if you don't have that, and tell me which one will be more negative, a salt crystal made out of KBr or a salt crystal made out of CaSe. And I can go look up the test. Oh, I can go look up the test 4 folder right now while you do that. So the first problem set for test 4 was 10:30, then it jumps to 11:06. So there's only 7 problem sets for this test. So the shortest amount on any test. Right, give about 20 more seconds. All right. So it's good that we have this type of poll because it seems there's a little bit of confusion of what does negative lattice energy mean. So let me get this set up right. So let's just look at our 2 different cases. We have KBr and CaSe. If we look on the periodic table, our metals are K and Ca, and our nonmetals are Br and Se. If we look at the sizes are about the same. Br is a little bit smaller than Se, but they're relatively the same. So the thing that comes down to this is charge. K has a +1 charge, Ca has a +2 charge, Br has a -1 charge, Se has a -2 charge. We know that by looking at our periodic table. So negative lattice energy is favorable. It's a good thing. If you have negative lattice energy, that means you're being held together very strong. Because forming a crystal always releases energy. And when you release energy, that's negative. So really, when it says more negative lattice energy, that is what has the stronger lattice energy, or what makes the stronger crystal? Well, that would be CaSe, because even if you look at the sizes, they're relatively the same sizes, but Ca and Se have bigger charges. And so CaSe is about 4 times more negative than KBr would be. So it's very hard to break apart a CaSe crystal, which means in terms of energy has a more negative crystal lattice. Is it correct to say that CaSe is closer on the periodic table than KBr? That's not what you want to look at. You want to look at their charges, right? That's more important than that. For example, you could look at why. So if I was going to do this, let's do. What if I was comparing Scandinavium to Se? So Scandinavium, let's say usually it only has a +1 charge. The CaSe would have a more negative lattice energy because of the charge. So you can't just look at the positions. You have to know the charges, because Se is closer to Se than Ca is. All right. So that's it for our lattice energies, and that's it for our ionic compounds in Lewis structures. What we're going to move on to now is looking at covalent structures. So let me pull up that PowerPoint. Okay. So today we're going to work on writing the Lewis structures of molecular compounds now. So Monday was ionic compounds, today is molecular compounds. And the basic steps for this are that you need to write out the right skeletal structure for the molecule. And by that, like, what order are the atoms in this compound? So some rules of that are hydrogens are always at terminal or end positions. Hydrogen will only be bound to one thing. And this is a common mistake. I often see people, when use hydrogen, they'll have it like bound to 2 things. That never happens, ever. Hydrogen will only be bound to one thing, and it's always like at one of the terminal ends of the compound. If you have multiple atoms, your electronegative atoms are placed at the terminal positions. So, for example, if you had carbon and chlorine, a lot of the times people have like chlorine bound to a bunch of things like this. That again is incorrect. Chlorine are usually at terminal positions, and like chlorine, fluorine are only usually bound to one thing. Another rule here that's not listed, carbon is usually in the center. Not always, but a lot of the times when you're working with carbon, that thing goes in the middle of your compound. And when we're doing this, we want to always be aware of the number of electrons for our Lewis structure, and that we have the correct number of electrons. When doing these, it's often I see people not include all the electrons, or they include more electrons than they should. For this, we are only given a set number of electrons to play with. Those electrons are determined by valence electrons of every atom in the molecule. So when putting together these structures, make sure all the electrons are accounted for. You cannot leave off electrons. You cannot add additional electrons. If you have charges, you have to account for those as well. Negative charges, you gain electrons. Positive charges, you lose electrons. When deciding where electrons go, you have to give octets to as many atoms as possible. There are some circumstances where atoms don't get a full octet. And remember, when I say the word octet, I mean 8 electrons. There are circumstances where that happens, but it's rare. Most of the time, you want to give electrons full octets. Hydrogens, they get duets, or hydrogens only need 2 electrons. Every other molecule needs 8 electrons. And if you find yourself in a position where you have atoms that don't have an octet, but you are out of electrons to place, you need to start forming double bonds and triple bonds. So just a review, remember a single bond, I'm just going to call that SB, a single bond, you share 2 electrons. A double bond, you share 4 electrons. A triple bond, you share 6 electrons. So the way to get molecular compounds to a full octet is that you sometimes have to add double bonds, sometimes you have to add triple bonds. So let's see if we can apply all those rules to making Lewis structures. So I'm going to do A for us. So I need a Lewis structure for SCl2. So I'm just going to write out my Lewis symbols to begin with. And hopefully we're comfortable with this now. So S has 6 valence electrons. Each chlorine has 7. Now I have to write my my skeleton. And I've seen stuff like this before, and that is not correct. Remember, electronegative atoms, and we talked about this term already, but I will repeat it. Electronegative equals really want electrons. So your halogens are really electronegative. They really want electrons. And the more electronegative you are, the more likely you're going to be at the terminal. So actually, I should not even draw that bond to begin with, force of habit. So to begin with, our skeleton looks like this. You have S in the middle and Cl on each side, right? Now I'm going to redraw my electrons like I did for my Lewis symbol. So chlorine gets 7. Chlorine gets 7. Sulfur gets 6. And I'm going to draw them in such a way to make it obvious. All right, so right now we have 7 electrons around chlorine, 6 electrons around sulfur, 7 electrons around chlorine. And I need these atoms to have a full octet. I need these atoms to have 8 electrons around them. But I have no more electrons to give because if I look at my Lewis symbols, I only have 20 electrons in my Lewis symbols. Right now, I have placed 20 electrons. So I cannot just randomly add electrons. So the way to solve this problem of not having a full octet is to add covalent bonds. So I'm going to make a single bond, and I'm going to use 2 dots. You can draw a line for a single bond here. That's fine. I like to keep dots. I'm going to draw a single bond, which is right there, from my chlorine to my sulfur. Now I can count, before I move on, let's count how many electrons are now around my chlorine. I have 2, 4, 6, 8. So I have 8 electrons around my chlorine. So that chlorine is good. Whoops, deleted too much. Sulfur, I have to associate with the other chlorine as well. So I'm going to make another single bond to my other chlorine. My other chlorine now has 8 electrons. That's a single bond. Now let's look at my sulfur. My sulfur has 2, 4, 6, 8. So my sulfur also has 8 electrons. So remember, in a covalent bond, you share electrons. So you get to count those pair of electrons for each molecule. So now I have a full octet for every single atom in my compound. And I've only used 20 electrons. I did not add more electrons. The chlorines are at the terminal positions because they're more electronegative. So that is the structure of SCl2. It goes Cl, S, Cl. All right, so hopefully you're able to follow that explanation and use that explanation of how we did SCl2 to try and figure out the Lewis structures for our other molecules here. So see if you can get through that. If you have questions about what I did there, please let me know. Or if you have questions, let me know as well. Yeah, other than that, I'll leave you to it and give everybody a couple minutes to try and figure out B, C, and D. So let's do NF3 in case people are still a little confused. Nitrogen has 5. Fluorine has 7. So fluorine is a halogen, so it's electronegative, which means it wants to go on the outside. So I just redraw my molecule with the number of electrons it has, each individual one. And let's count up the number of electrons I have. So nitrogen currently has 5. Each fluorine has 7. So that's not good. Nothing has a full octet. So let's start making bonds. So if I make a bond between that fluorine and that nitrogen, so I'm showing the bond by the line, my nitrogen goes up to 6 and that fluorine goes up to 8. So that fluorine's done. Make a bond here. So that nitrogen now has 7 electrons. That fluorine has 8 electrons. So that fluorine's good. Make another single bond there. Now my nitrogen has 8 electrons. My fluorine also has 8 electrons. That's good. My nitrogen's good. So that's what it looks like. Nitrogen in the center, 3 fluorines around it, making single bonds. Everything has 8 electrons. My electronegative fluorine is on the outside. So that is NF3. All right, so let's do C. Carbon, again, carbon, I never like pair up the electrons because carbon loves the bond so much. So I always put electrons in each spot. So we have carbon. Hydrogen has 1 valence electron, and we have 5 of those. Nitrogen has 5. All right, so here's a secret on how chemists write stuff with hydrogens. A lot of the time, they will tell you how the hydrogens are bound. So carbon gets 3 hydrogens. Nitrogen gets 2 hydrogens. That's why they wrote it like that. They're telling you how it's bound. And remember, hydrogen only binds to one thing always. If you are ever tempted to put hydrogen bonded to 2 things, I'm going to tell you right now, you're wrong. Don't ever do that because you will get it wrong, and that's not correct. So carbon is usually in the center, and it gets 3 hydrogens. Then the next thing is nitrogen, because hydrogen never goes in the center. So nitrogen comes with 2 electrons. I kind of just sped it up there. But that is our structure. Carbon has 8 electrons around it. Nitrogen has 8 electrons around it. Hydrogen has 2 electrons around it. Remember, hydrogen can have 2 electrons. It's one of the few elements that does not need an octet. So that is the structure for CH3NH2. And then lastly, I'm going to do D quick here. Let me get some space. D, we have carbon, fluorine, which has 7, chlorine, which has 7. And there's 3 of those. So again, electronegative fluorine and chlorine don't want to be in the center. And halogens usually only bind to one thing as well. So again, if you are tempted to have one of your halogens bind to 2 different molecules, you're wrong. Don't do that. Never have your halogen bind to 2 things. Always put your carbon in the center because that's normally right. So there's our carbon with our 4 electrons. And I'm just going to go around and add my halogens. And I'm going to write the number of electrons they get. So right now, carbon's at 4, fluorine's at 7, chlorine at 7, 7, 7. So let's make our bonds. Make a bond there, carbon's at 5, fluorine's at 8. Make a single bond there, carbon's at 6, chlorine's at 8. Make a single bond there, chlorine's at 8, carbon's at 7. Make a single bond here, carbon's at 8, chlorine's at 8, and we're all good. So here, carbon's in the center, bound to 4 halogens, and that is our structure for CFCl3. Doesn't matter where we place the hydrogen in carbon, like I put it on top and still connected to nitrogen. It will matter in a couple of lessons from now. Right now, it doesn't matter. Right now, what matters is what you connect them to. Then we're going to learn in a future lesson exactly how to place them in what geometry. But right now, I'm not worried about that. Setting carbon aside, what determines what atoms goes in the center? Electronegativity. Basically, the less electronegative you are, the more likely you are to want to be in the center. So carbons are in the center, nitrogens are in the center, sulfur, phosphorus, silicon in the center. Things like oxygen, usually not in the center. It can be sometimes with ether bonds and ester bonds, different types of bonds, but usually oxygen, not so much. Fluorine, never. Chlorine, never. Bromine, never. So the less electronegative you are, the more likely you're going to be in the center. Basically, carbon's always in the center. And remember, with covalent bonds, we're only looking at a few elements. Metals aren't involved in covalent bonds, really. So we're just looking at the small area of the periodic table. So if you just remember, like carbon, silicon, nitrogen, usually in the center, phosphorus, usually in the center, you'll be good. Halogens, not in the center. Right, any other questions? All right. So the next thing we're going to look at is this idea of electronegativity. So we said, atoms that are electronegative want to get more electrons. We talked about this already a little bit last week, but we actually can assign scores to this. Now this table, I will probably give people this table. Excuse me. So you don't need to memorize the numbers. But you do need to know how to read this table. So this is how much an atom wants to get an electron. The maximum number this table goes up to is 4 for fluorine. So fluorine is your most electronegative atom. It wants electrons the most. Francium is your least electronegative atom. It does not want electrons. So electronegativity increases as you go to the top right of the periodic table. Now, when you are looking at bonds, you can look at the electronegativity difference between atoms and determine what type of bond they're in. So if the electronegativity difference between two atoms is 0, you're in a pure covalent bond. What I mean by that is, let's say two carbons are in a covalent bond. The way to figure out what type of bond they're in is you look at their electronegativity scores. So carbon has a score of 2.5. The other carbon also has a score of 2.5. What you do is you subtract those two numbers. So 2.5 minus 2.5 is 0. If the electronegativity difference is 0, that is pure covalent. That is, the electrons in that bond are shared 100% equally. No atom has a greater share of that bond. If it's between 0.1 and 0.4, we call that nonpolar covalent. That is, you're in a covalent bond and you still share your electrons pretty equally. So an example there would be carbon and selenium, carbon and Se. So carbon has a score of 2.5, selenium has a score of 2.4. You subtract the two and it's 0.1. So they're in a covalent bond and they share the electrons equally as well. Maybe not 100% equal, but close enough that it doesn't make a difference. And let me just say right now, you cannot get a negative score for this. So if you were to